In this podcast, we're going to talk about the thymus. Before I talk about the thymus, though, I want to say a few words about lymphoid organs in general. And first of all, you need to understand that the lymphoid organs provide the microenvironment for the cellular functions of the adaptive immune system. We can classify lymphoid organs as either lymphoreticular or lymphoepithelial. Lymphoreticular organs would be organs like the lymph nodes, the thymus, and the spleen. And in this case, these organs have a network of reticular cells or stromal cells that surround the parenchymal cells. And now in this course you're going to hear the terms stromal cell and parenchymal cell fairly often. The stromal cell is a connective tissue cell that provides the structural basis for organs, whereas the parenchymal cell is the functional or business cell of an organ. So we define lymphoreticular organs, the lymph nodes, thymus, and the spleen. We contrast these to lymphoepithelial organs. In lymphoepithelial organs, lymphocytes associate with an epithelium. They can contact or colonize the epithelium. So gut-associated lymphatic tissue or bronchiola-associated lymphatic tissue in the form of nodules, or mucosal-associated lymphatic tissue, which is more diffuse, would all be lymphoepithelial type organs. So organs like the tonsils, the Peyer's patches, or various lymphoid nodules that you might find in the appendix, in the GI tract, the urogenital tract, or the respiratory tract would be lymphoepithelial organs. Let's talk about the thymus for the remainder of this podcast. As you know from gross anatomy, the thymus is located in the mediastinum in front of the great vessels of the heart. In the embryo, the thymus originates as separate primordia that fuse. The thymus achieves its greatest relative weight at birth, although the weight of the thymus increases throughout puberty. The adult thymus is mostly invested with adipose tissue, but in humans and other primates, the thymus is functional. I put a red question mark here because for a long time people assumed that the thymus was not functional in adults, and they based that reasoning on studies done in rodents. If you take the thymus out of adult rodents, the animals seem to live a normal life with a normal immune function, but of course rodents don't live that long. If you take the thymus out of an adult primate, you're going to compromise the immune function of that primate. So we think now that the thymus, although mostly invested by adipose, is functioning in adult humans. The thymus is the first organ to acquire lymphoid function. It's seeded by stem cells from the yolk sac and then from the liver and bone marrow, so the thymus is a primary lymphoid organ. As we know, T lymphocytes develop in the thymus. As shown on this cartoon, there's a connective tissue capsule that penetrates the organ. The septa subdivide the thymus into lobules. There is a darker peripheral cortex, a lighter central medulla. It's in the cortex that there are many T cells that are developing and differentiating within the thymic medulla. There's a diagnostic feature that we give the term Hassel's corpuscles. I'll show you those histologically later. There are a variety of epithelial reticular cells in the thymus. Some of these are unique to the cortex and some are unique to the medulla, and some of these thymic reticular cells also form these Hassel's corpuscles. The thymic cortex is composed principally of T lymphocytes at various stages of development. They're either undergoing clonal selection or clonal deletion. The largest, most immature lymphocytes are towards the periphery of the thymic cortex. You might often encounter mitotic figures. Most cells at the center of the cortex and in the medulla are degenerating, either undergoing apoptosis, clonal deletion, or inactive activation clonal energy. There are also abundant macrophages and antigen-presenting cells found in the thymic cortex. T cells develop in a stromal network. These stromal cells or reticular cells in the cartoon are highlighted in blue. They're stellate-shaped cells. They put out these long projections that join one cell to another through desmosomes. We know these are epithelial cells because if you do cytochemical stains for keratin, you'll identify keratin in these stromal cells, and keratin is a protein uniquely found in epithelial cells. In the electron micrograph, you see these bundles of tonofilaments. These tonofilaments or tonofibrils would stain positively with keratin. And then the micrograph shows T cells developing in the thymic cortex. There are at least 6 distinct types of thymic stromal cells, 3 that are unique to the cortex, 3 that are unique to the medulla. All of these are thought to play a role in the development or education, if you want, of T cells. Some of these thymic reticular cells function as antigen-presenting cells. Others secrete various cytokines that are going to play a role in either clonal selection or clonal deletion. In your readings, you'll encounter terms like thymosin, thymopoietin, thymulin, thymic humoral factor. These are all cytokines secreted by the thymic reticular cells. The thymus does not have any lymphatic vessels associated with it. What this diagram is highlighting is how the blood supply gets into the thymus, and it's also highlighting here T cells that are developing in the thymus that have to migrate through the cortex into the medulla, where these T cells will enter the blood supply. T lymphocytes migrate through the cortex, they enter the blood supply through venous capillaries, and they take up residence in other lymphoid organs, the so-called thymic dependent areas of the other lymphoid organs, or they become surveillance T cells in the peripheral blood. As you might expect, arteries enter the thymus through the capsule. They branch and they penetrate the organ following the connective tissue septa, as we showed earlier. The arterioles leave the septa and they'll penetrate the parenchyma of the thymus along the border of the cortex and medulla. And these capillaries will branch, they'll penetrate into the cortex, and then come back into the medulla, where they'll drain into venules. We define something called a blood-thymus barrier associated with the capillaries in the thymic cortex. We define this blood-thymus barrier because the capillaries in the thymic cortex have non-fenestrated endothelium, they have a thick basal lamina associated with them, and they are surrounded by thymic reticular cells in the cortex. Why do we invoke the concept of a blood-thymus barrier? We invoke it for this morphological evidence that we've described, the non-fenestrated endothelium, the thick basal lamina, and the reticular cells surrounding the capillaries, but we also invoke it to explain why we think thymic T cells are not self-reactive. That is why they're not reacting against molecules of the body itself. 80 to 90% of the T cells in the thymus are undergoing apoptosis or clonal deletion, because 80 to 90% of the T cells in the thymus would be self-reacting T cells. Only 10 to 20% of the T cells that develop in the thymus would be self-tolerant, and it's the self-tolerant T cells that undergo clonal expansion and become functional T cells that enter the general circulation as either surveillance T cells or to take up residence in other areas, other thymic dependent areas in the body. When this breaks down, when the self-reacting T cells actually undergo clonal expansion and get into the circulation, that's when you develop autoimmune disorders. So what we can first say is the T cell education depends on interactions with the various thymic reticular cells. There are colony-forming unit stem cells that seed the thymus from post-capillary venules. These colony-forming units will migrate from the medulla into the cortex, and it is in this region that these cells will start interacting with epithelial reticular cells. Here, remember, this cartoon said these cells are maturing and then migrating back into the medulla where they'll enter the general circulation. So the colony-forming units coming from the post-capillary venules get into the thymic cortex, and they will mature in the thymic cortex. When they're matured, they will then pass into the general circulation. And they will pass into the general circulation either as mature helper T cells that are expressing CD4 or cytotoxic T cells that are expressing CD8. There are, as we said, a variety of epithelial reticular cells found only in the thymic cortex that are type 1, type 2, and type 3 cells, or there are epithelial reticular cells only in the medulla of the thymus, type 4, type 5, and type 6. Type 2 and type 5 are critical for T cell selection, and here showing the distribution, thymic reticular cell type 1s near the boundary of the cortex of the thymus. Here are the type 2 cells playing a role in T cell maturation. Here are type 3 cells and type 4 cells near the border of the cortex and medulla. Type 5 cells in the medulla playing a role in T cell selection. And then the function of this type 6 cell may be not so well understood. The thymic epithelial reticular cell, the type 6 cell, might be the ones involved in the formation of the Hassel's corpuscles. So what this cartoon is showing is you've got these immature T cells that are interacting and expressing various CD markers and T cell receptors on their cell surface. They're cross-talking with the thymic epithelial cells. They're undergoing various processes of selection. Those that pass the selection enter into the medulla where there's additional CD markers expressed and additional T cell receptors expressed. These interact with type 5 thymic reticular cells, and these T cells will mature into the functional helper or cytotoxic T cells. This is a very complicated slide, well beyond the scope of our course. Let me just make it simpler here and just say we believe the T cell education in the thymus is positional dependent as T lymphocytes interact with the various thymic reticular cells under the influence of various transcription factors and various cell signaling pathways. So the blood-thymus barrier prevents the T cells in the thymic cortex from entering the general circulation. It allows for T cell education and selection so that self-reacting T cells are either eliminated or inactivated. The self-tolerant T cells now would be the ones shown by these big bold black arrows that are going into the thymic medulla and ultimately entering the blood through the capillaries in the thymic medulla. With appropriate signals, naive T cells will undergo education or selection in adults. So we think that there is always a little bit of recruitment of T cells in the thymus, and perhaps there are stem cells in the bone marrow that make their way into the thymus and will undergo the process of T cell selection as individuals are older and older. Here are some histological views of the thymus. The cortex stains darker because there are large numbers of T cells in the cortex undergoing maturation. You might imagine these lymphocytes have abundant rough ER to synthesize the cell surface proteins on the T cells that are involved in both positive and negative selection. Here, just a little bit higher power view showing the cortex and the medulla, and a very high power view showing these Hassel's corpuscles. The lymphocytes in the medulla are self-tolerant, and those are the ones that will finally enter the general circulation. The Hassel's corpuscles in the medulla consist of these concentric rings, most likely of type 6 thymic reticular cells. They probably have keratohyalin granules. They probably calcify and die. They may or may not be involved in T cell selection.